Hello, community. Today we talk about what is the next frame in AI. And of course, we talk about AI agents, multimodal, autonomous, drone systems, and so on. So here we start. Now, you know that I had quite some videos about the science of AI agents, about interactive LLM agents, what is the best LLM system for an agent, about how to create simply from one prompt, three interacting agents, and so on. You know this as a subscriber of this channel. Then, there was this bunch of videos about data science, where we used GPT-4 code interpreter or the data science engine. I showed you how to further fine-tune here, for example, the wizard coder, 34 billion pre-trainable parameter model. And I showed you here also for the connectivity of agents to connect an LLM to an API or have a rapid API as a tool, as an LLM tool here available for you for the interconnect of agents. And then in the last weeks, I showed you if we have here the language model, the LLMs, our large language models, we are missing here the mathematical formulas. So they are now AI system trained to extract here from the text any mathematical, chemical, biological formula, anything that is not simply plain English text, but has some integral or whatever. And you can extend this not just to the scientific notation, but in general to almost everything we see in an image, in a PDF, or whatever. And then we have here, if we say this is here the language part, this is the coding and the API part, of course we went here to vision transformers. I told you that here the language transformers are transformer based and the vision transformers are transformer based here. So this is beautiful because we have the same architecture of our models. So this means we can use here the knowledge here of coding these models to code here vision transformers. And I have several videos here on BLIP2, for examples. And for the data, to generate synthetic AI data for scenarios where you have here a vision where multiple helicopters, for example, interact, we created here, or I showed you how here the Air Force created here synthetic AI data sets for vision. And then there was this short period of time, everybody was talking about a vector database where you have here with your LLM only having, 32K token length or 64K token length. Everybody said, hey, can we not just upload all our huge document to simply a database? And have a search algorithm where it searches here the database and only the search result of the database are returned here to our LLM. And I showed you, take the database, build an AI, let an AI learn the content of the database. And then we have some multi-AI system here. This was this step. And also in the last week, we were talking about here on stable diffusion, on control LoRa elements here in text-to-image generation. You noticed also that in the GPT-4 prompt engineering, I had some videos of chain of density to make here a summary more informative. In every iteration, you make it more informative, you put in more data, you make it more compact, you increase the information density of an AI summary. And we used for this, I showed you a trick that we use here a knowledge graph analysis of the text. And having identified the nodes and the edges of the knowledge graph, this identity becomes so much more faster, cheaper, and much more beautiful from the content. I had some video here on reasoning here. I showed you from the chain of sort to the graph of sort. So we operated here with graph structures. Again, like here in the knowledge graph. And then I showed you here the interlink here between our LLM models and the interlink here to the graph machine learning to predict patterns here in a graph structure. So I would call this here my graph element. And of course, you say, hey, you're missing out here on the extension of language, vision, code. And then here we are now living in our environment, and we have now robotics objects that move in the real 3D world. And this is here the videos. I did 5 videos on AI robotics, where I showed you that Google is maybe currently one of the major players that also publishes research papers about this. So as you can see, this here is more or less here the main trends currently in artificial intelligence. And you might say, hey, a little bit more structure, please. Are there symmetries? Are there dependencies of this? Well, of course. So let's see this on a meta level, on a higher level. So we have here in this area our LLM, our large language models, and whatever is not text in the large language models, like mathematical integral forms or tables or physical or biochemical molecular visualizations. We have Nougat, specialized on mathematical formula. Great. Then, as I told you, we have here our coding LLMs. We have a lot of LLMs that were trained to code. And for example, with Code Interpreter, we saw that this system was attached to a virtual Python environment, and it could execute within this Python environment really the Python code it generated. But we also noticed that this environment does not have all libraries, does have only a limited compute capabilities. So I think the next step here will be to make this here extendable. Of course, maybe it will cost a little bit more money, but then we can upscale here the compute infrastructure for our virtual Python environment with our coding LLM. So this is a clear trend that's going to come in the next month. Here, as I showed you, we have all now the vision LLMs. So our normal LLMs, and now we add here all the vision information. And this was here the time. Look at the picture. Tell me, what is the content of the picture? Do you see one helicopter? Do you see 5 people? So here, the combination of vision and language, because as human, we are very heavy depending on the vision. And then, of course, when we have language and we have image, we have now the synthesis of this text to image generation, like Stable Diffusion, where we write some text and an automatic and image is generated by an AI. Please notice that we have here a control loop. So we have here an LLM, so text is generated. We insert this text here into, let's say, Stable Diffusion. So from the text from an LLM, we generate an image. This image we take, we put it here as input to our vision LLM. The vision LLM tells us, hey, I can identify 3, 4, 5 objects in this image, and we get a verbal text, a textual description of the content of the image. You can chat with your image, and if you have this now in a training loop, you see that you really can combine here the semantic content of language with the vision, and this depends not on the sensor. I showed you how a multi-sensor combination of infrared, LiDAR, the visuals, human detectable spectrum of light, radar, and so on. So this is here, this area. And of course, the moment we have here language, vision, we understand how this connects. We put our systems now out in the environment so that they can interact with the environment and become part of the environment. So here we have my videos on AI robotics. So you see, it all comes together. But you might ask, hey, what is missing? What is coming up in the next month? Well, I personally think we will have here in some way here a connex to the graph machine learning. And I will show you why I argue here. Or if you want to be even more general, to have a physics engine. Because if we can compute here something, what we are still missing is here a complete digital twin of our environment. So we can compute in the digital twin, in the virtual environment here, all possible path forward for an objects. And this is what I mean with a real physics engine where we have the laws of physics here as the basis for our digital twin to see how a physical system evolves. But this is an outlook for the future. Let's take this schema and let's validate it. Let's see if it's valid. If we look here at a company, we take OpenAI as a company. Let's see, as you can see here, I'm recording this video on October the 3rd, 2023. So here we go, the same structure. We have here our GPT-4 LLM, since we're only looking here at the products of OpenAI. And then we have here, for increased privacy and your secure data, GPT-4 Enterprise, where you get a machine from GPT-4. And this is only your machine, and you have all the security standards and so on. Great. So here we have our LLM. I personally think, or I use here as an audio, I use Whisper. For me personally, in my knowledge domain I'm working, Whisper is the best audio LLM. And then, you know, OpenAI has here the GPT-4 code interpreter, or it's called now some data analysis tool. I think this is one of the best coding LLMs we have currently available if you look at the higher mathematical complexity or physical complexity of coding, and it also performs the Python code it writes, and it gives you back a result. Great. Now, in the mid of October 2023, we expect 2 new products from OpenAI. Here, this combination of vision and large language model, we will see GPT-4V for vision, and for the text to image, as I just showed you with Stable Diffusion, we expect in the next days here the release of Dall-E3. So you see, it's the same schema we have here, like the vision transformers. We have now, I showed you this already 6 months ago, a lot of companies tried this, published new research, published new code sequences, and now in the next days, OpenAI will release their product, and also this will be released here to the public if you want. So we hope these are really products that set new benchmark in this area. And of course, you know what's missing. And again, we have no integration of a graph machine learning here in the current product portfolio of OpenAI. Currently, we have nothing about the robotics integration, or we are even missing here, I think, the most important factor for the future, a physics engine, so a digital twin of our environment. Okay. But since I also want to talk with you about the development of agents and what are AI agents now in this particular portfolio and how they interact with each other, and given we have here language, given we have here code, given we have here vision, so we are definitely in a multimodal structure. And of course, video will come up in a minute. So for OpenAI, I think this is now the product portfolio with our language model, with the audio models, with the code models, with the vision and language models, and then for the control cycle here, the text to image models. These 2 are part of the future. Great. Yeah, very short what we know from here, very short research paper, GPT-4 vision. It will be a multimodal LLM. Now you have a notation of MLLM, or you have a notation of M3, multimodal model, whatever you prefer. Whenever you see this abbreviation, you know exactly what it means. So we have now text and image input, multimodal, of course, solve new task where every human has vision. So we orient ourselves looking at the world. And now this should also be possible here with GPT-4. Interesting, the complexity of the information capture. OpenAI claims, as I showed you, also imagery extracted from scientific publication and diagrams. So exactly what I mentioned, it was positioned here. Nougat here should also be included now in the new OpenAI product. Great. So Now I would like you to step back, look at this, and tell me, how many agents do you see in this image? Which agent can be connected to be multimodal agent systems? Easy. Whatever is a model is an agent. Whatever is a large language model is an agent. Whatever is a visual transformer can be an agent. Whatever is a visual language model can be an agent. Whatever is a visual language action-based robotics model can be an agent. Unbelievable. So agents are simply systems you have access over the internet. You have locally on PC. Maybe you have 1, 2 agents locally on PC. You connect to 1, 2, 3 agents over the internet or over some secure connection. You see, now we come to this area where simply we have here a combination of forces, a combination of specialized models, a mixture of expert systems. So this will be now our focus. And you might ask here, if you look here at complexity theory or mathematical theory, what is the optimal size of an agent in a multi-agent system? Now, you would say, hey, it's easy, no? If you look at a system of agent and you ask yourself, hey, what is the perfect data information connectome for a given amount of agents? How is their interconnectivity of the agent? What is the bandwidth? What can they exchange on data structures? What is their inherent complexity they have? And I mean here the compute complexity, including the cost of the compute infrastructure. What is their logical complexity? Think about vision language model or vision language robotics model. Well, it depends heavily on the task. What is the optimal size of an agent? Depends here on your specific task. So the perfect system configuration of a multi-agent system. So you have 2 GPT-4 systems, maybe 1 robotics system from Google. You have a coding system from OpenAI. This depends on the task, on the time you're willing to invest, how much money you want to have, how much resources you have also access to GPUs, what are your training data available, and overall the cost factors. Great. So let's take another step back and let's look at the future. Now, have a look here. I have here my language model, GPT-4 and GPT-4 Enterprise, and my code models. And let's say they are all in one monolithic block here, GPT-4. And then I have here my vision language model that are coming up in the next days, GPT-4V. I have my new text-to-image model, and I have my audio models. Now, if I give now, let's say these are 2 monolithic agents. I connect them in a way that they are 2 monolithic agents. You might ask, what system coordinates their steps of analysis? What system coordinates their data exchange? At what period in time do they exchange data? Do they agree on a common strategy to solve the task you give them? How can they enhance their performance with a specific interaction patterns? Step 1, step 2, step 3, step 4, step 5, 6, 7. How is the path forward in this complexity? Let's make it even a little bit more interesting. Let's say we have here in the future, we have GPT-4 video. Now it gets really interesting. Because for video, you have new problems coming up. You remember in the language model, it was easy. It was predict the next word in a sentence. We have an autoregressive model. This is GPT-4 or any other model, almost the same. The next word in a language in a sentence. With video, the task is now predict the next frame of a video. And since a video is a sequence of images, predict the next possible image, given here a specific time evolution, a time series of images. This information is not really available in the language model and not in the vision models. So what we used here in the language model, we trained it on the complete human language literature on libraries. So we give it all the information. This is also a possible way, but we are a little bit more clever now. So we can say, hey, for this video, we can reduce the vector space that we built with the implication of some logic. If we apply here some graph structures that have some actual facts, some data about objects, we can accelerate here our learning procedure significantly. So you see, language, we had the prediction, the next word or the next code segment or the next code element here in a code sequence. And vision was more or less find all the objects, the image or the segmentation, the object detection in an image, create from a text an image. This was not some, let's say, some prediction, but you just have to build it based on probabilities. But here, now with video, you have to predict the next frame of the video. This is here how you train this system. And this is now how it gets interesting. So I thought, how can I do this? And I went out in my garden, and this is the picture I took 2 minutes ago. Look, my sunflowers and the moon. So this is now one image of a time series of image, and this is the last image. And the task now of GPT-4 video is predict the next image, the next frame in this sequence of images for a specific video content that I want to generate a synthetic video from text. So what we do now, the next step, we have a segmentation task. So we say here, we take GPT-4 vision, our vision LLM, and say, hey, identify all objects that you can identify in this image. And GPT-4V, which will be released in some days, will tell us, hey, this is the moon, this is a sunflower, this is a sunflower, this is a sunflower, this is the sky, and this is some tree and whatever. So this we can do. But how do we come now from this to the next frame? Now, what is the possibility? I'm living in Vienna, so there could be, and Vienna has an airport, a plane passing by. Here, an object that is possible in the next frame. You might ask, hey, is this possible? A happy orca swimming in the sky? No. So how we decide this for the prediction of the next frame? What system can we use? Let me give you 2 very basic examples. At first, we can have a knowledge graph. We have a node orca and we have a node ocean. And our edge has some attribute, and the attribute of the edge is here. The orca lives in the ocean. The simplest graph you can imagine, 2 nodes, 1 edge. Another possibility, as we did with the language, was you can connect now to a GPT-4 large language model and ask GPT-4, hey, given our language, our semantic information that we store in a language, in a sentence, tell me, what objects are detectable in the sky? And is an orca part of an object that is detectable in the sky? And from the knowledge we encoded in the human language, GPT-4 will come back after some times and after some costs and after some delay and after some whatever and tell us, hey, no, orcas are not expected in the sky, given here our language knowledge. But if I have here just a simple knowledge graph, I don't have to connect to GPT-4, I don't have to pay for GPT-4, I don't have to wait for the execution in GPT-4. I can make it so much easier, say, orca lives in ocean, knowledge graph, fact, done. And I can, of course, reverse this. I can simply say, hey, I have here identified the sky as the main object here in the background. Give me now all the objects from a knowledge graph that are detectable by vision in the sky by humans. Can be an aeroplane, a bird, a balloon, the moon, whatever. So you see, with this method of a graph structure, we can reduce the possible complexity of a vector space, what is flying in the sky, to very, very limited set of objects. And I think this is the way forward. Theoretically, you could access now the language knowledge over GPT-4, but the latency is high, the costs are extreme, and whatever. So you see, I hope this is an example that you see what I mean with the integration of logic and graph structure, graph machine learning, and GPT-4. For here, the video prediction task of predict the next frame of a video. Great. Yeah. Now, having this structure and having those three now elements here that have the ability to solve a specific task. Here, we can generate a synthetic video, just give them some verbal description. Here, we can detect all objects in a frame, in an image. And here, you know, your good old GPT-4 LLM and code interpreter that is also based on characters. If we want to combine those with an agent, what are the requirements for an agent? How you have to build here the data exchange between your monolithic intelligence system, and why do I think that you need here a central intelligence for the coordination if they exchange data in a specific time period of the task solving a problem. I think it will be here the need for a huge monolithic system like GPT-5 that will serve as a central intelligence that will decide, given a specific task. Okay, we have an input from a language and we have an input from an image. So I will activate this, I will activate this, I will bring them together. I will see what is the result of both of those intelligences. Then I can say about time series, I can have some code interpretation. How will the objects in this vision evolve? For example, if a human enters a swimming pool, in 5 seconds later, when the human will leave the water, will the human be dissolved like a piece of sugar? No. So we have object identifier, object characteristics we can apply here from maybe some physical engine, or in the simplest case, for some graph machine learning. And you see, this is the way forward to solve some complex tasks, having here the combined of intelligence of specialized expert system given in language, in vision detection, in audio, in video, in logic, and so on. We can code it, we can simulate it, we can build a digital twin, we can verify this simply by looking then at the result, either in language or in vision or in video output, and have here the control cycle again. So you see, in 2023, we had more or less the task to predict the next word of a sentence. And I think 2024 will find us here to predict the objects in the next frame of a video, about the movement of objects in this frame, what new objects can emerge. If we have a physics engine, we know how those objects can move, can shift, can rotate, can become bigger or smaller, perspective correlations. Everything of this, I think, will be a topic of research in beginning of 2024. And I think it's an amazing time. It's an amazing research area. We can integrate everything what we know from physics. It is unbelievable. And I hope I ignited a little bit of a fascination for the upcoming AI system in our near future. It would be great to see you in my next video.